Hi, and welcome to another video in the series on how to get the Hopper runtime up and running and get developing Hopper programs on a 6502 8-bit microprocessor using the RetroShields from 8-bit Force. So there it is, 6502 RetroShield. And in this video, I'm going to explain how you get how you build the firmware, so how you will build the runtime for this device, and how you're going to get it onto your Arduino device. Right, so there's two ways you can do it. You can do it with one of these Teensys on it's on an adapter board that is the same form factor as an Arduino Mega, and it's a pretty cool device because it's pretty fast for an Arduino device. It runs at 600 megahertz, but it's also not cheap. It's like, about $30 or so. That's with the pins already soldered. You can get, do a little bit of work yourself and get the cost down a bit. And another way you can do it is you can do it using, so this is the RetroShield. You can buy this adapter. So in addition to the Teensy, you have to buy the RetroShield as well. You can get it assembled as well. But the other way to do it is to use an Arduino Mega or clone, which is a lot cheaper because you just buy one of these instead of and they $10 instead of 18 plus 28. However, it's slow. It's only 16 megahertz. So the fastest your 6502 is going to run is going to be about 100 kilohertz, whereas on the Teensy it can run at full speed at 1 megahertz. And it also has very limited RAM. So that means that on your 6502, I think you're only going to have about 6K of RAM. Whereas this one, since we've got the runtime squeezed into 8K of ROM, you can have as much as 56K of RAM. So pretty big Hopper programs. Right. So let's get started on this. In the previous video, you've already seen how you download and install the runtime. So we're going to assume you've got that far already. So let's go to the Hopper IDE where we left off. So we did the little Hello World program. Now, a word of caution, you're going to be all keen to plug your RetroShield in. Don't do that. So until you've actually got the firmware on the Arduino style device, it's not a good idea to plug in the 8-bit CPU because you don't know what the pins are by default. The pins connected, the I/O pins connected to here are going to be by default. So it's better to have the firmware running already so that the pins are at safe values, like sensible values to, host and drive the 8-bit CPU. So with no shield on the device, I'm going to plug it in. It's not going to do much. There we go. It'll sit there with a nice little red light for a while. And then inside the Hopper environment, which you've already learned how to set up, we're going to go to the runtime folder. And in this runtime folder, there's an assembler file called r6502.asm. And if we open that in the editor, and you don't have to put the extension on, it looks a lot like Hopper code, but it's not. It's got an ASM extension, and it's actually 6502 assembler. And my 6502 on my shield is an original MOS 6502, not a Western Design Center 65C02S. It has a smaller instruction set, so you've got to specify that before you build in this IDE. So this is going to build the runtime for us, the minimal runtime. There's a video in this playlist explaining what the minimal Hopper runtime is compared to the regular Hopper runtime. It's part of this playlist right at the end. It's a little bit more detailed. You don't really need to know about that right now. So according to if we look at the bottom of the screen, we've successfully built the runtime, and it's created a hex file. And it's you could use this hex file. If you weren't working with the RetroShield, you could use this hex file to burn an EEPROM, for example. But we're working with the RetroShield. So if we go to the bin folder, oops, and we do dir, what's it called, runtime 65, yeah, something like that. We've, in addition to the hex file, there's also a C file. So let's go and have a look at that. In here, there's a C file, right? And I'm just going to open that in Notepad++, like so. Okay. So what that C file is it's a sort of a C version of that hex file. It's just the binary of the runtime, and it's less than 8K. So it's loading its origin in an EEPROM would be at hex C00. It's actually 16K, but it doesn't matter. It must have a lot of zeros in the bottom. Yes, it does. There's a lot of zeros. And then right at the end, it's got the vectors. So those are the vectors for non-maskable interrupt, etc. Yeah. Okay. So I'm going to copy that, Control-C, and put it on the clipboard. And then, oh, I've just been doing this all on the other screen. Sorry about that. Let me show you my full screen and just repeat what I said. So I went and found that same file in the bin folder, loaded it into Notepad. Its origin is at 48K. It's got a lot of zeros in it, so there's a lot of space for more. This is actually a 16K ROM. Could have been an 8K ROM. Okay. Anyway, I'm going to copy that onto the clipboard. Go back to there again. Now, under runtimes, there's something called Arduino. And under Arduino, under 8-bit force, there's two. And there's one for the Mega. So you would use the same steps to flash the firmware on the Mega as you, more or less the same steps as you do on the Teensy. And then the T1 is for the Teensy. So this is the Teensy firmware for Arduino. So we'll double click on that. Launch the Arduino IDE. And then we're going to go choose a board. So our board is, in my case, it's a Teensy 4.1. And then Teensy is kind of peculiar in terms of ports. It's got its own way of doing ports. So we're going to choose that Teensy port. And this file here, the ROM image, is I'm going to select all and paste over it from my clipboard. So I'm putting the new version in there that I've just built. And then all I have to do is build and upload. Let's see what happens. So it launches, it brings up this Teensy dialog. So it's got its own communication here. And it says it was successful. It's uploaded successfully. I think I can do, what do we do? Desktop in the video. There we go. So yeah, it's successfully uploaded. All right. So I've got it on the device. So I can close all this. I'm done with it. And we can switch back to just our screen, this one. So let's check. We'll look and see if we've got serial ports. We do have a serial port. And now there's something called the Hopper monitor, which is a sort of low-level debugging interface with the device. So let's launch that. Takes a little while to figure out the ports. Yeah, a little bit of light flickering happened. There we go, Hopper Mon. It didn't actually work. Why didn't you launch? Try that again. Have you tried turning the power off and on again? Yeah, let's try that again. Oh, I know why. Clues as to why that didn't work? Pretty good reason. I never plugged in my CPU. I don't know what's wrong with this picture. All right, let's try that again. All right, so we've now got a 6502 plugged in, so the 6502 code might actually run. All right, pretty forgiving, isn't it? There we go. There we go. That's better. So now if I look at, I can do, look at the 0 page. If I type question mark here, it will tell me all the features of Hopper Mon. It's got a neater way of looking at the 0 page. I can try and run a program, but it'll tell me there's nothing loaded. No program loaded. Right, so let's go make ourselves a program. CD, that way, CD, source tree in Hopper is pretty big. It's got lots of stuff in it. Under testing, under minimal, Let's see what we got here. Ah, yes, let's look at the Fibonacci one. Fibonacci sequence program. So there it is. It's going to Fibonacci 10, which will be 55 should be the answer. So are we building? Yes, we're building for the minimal runtime. There we go. And yeah, this will build. So F7 to build, pre-processing, etc. all built. And now if I go back out again and I run the Hopper monitor again, I can now say load Fibo. Load up the Fibonacci. It says it's loaded it. Let's look at the source. Yep, there it is. So source level debugging. This debugger is designed to debug the opcodes of the Hopper runtime rather than Hopper. But if I F5 here, it'll run a bit slowly because it's looking for breakpoints. So there it succeeded. 55 in 1 second, Fibo 10, Fibonacci 10. So that worked. And then if we go back and edit here, and if we F5 over here, this will run the full debugger. So at the bottom of the screen, uploading, successfully uploaded. And here, if I run in the debugger, I can F5 and it'll all just run. There it goes again. This is the serial connection over here. Or I could start again and just step in. And you can see I'm stepping through the code. And it is right now stepping through the code on the 6502. And let's get rid of that video. So you can see on the right hand side here, there's a call stack, and I can jump through the call stack. I can put in a breakpoint, hit F5 and run to the breakpoint. There we go. We've stopped at the breakpoint. We've got some variables in here. Start and current time. The time's going to be a little longer than 2 seconds this time, obviously, because we're stopped in the breakpoint. And we can step through the code, and we'll get the printout over here. 34 seconds because we stopped in the breakpoint. Anyway, there you go. We're up and running with running Hopper code, which is, quite a modern semicolon curly brace language with strings and arrays in the middle in the minimal runtime. So pretty much the power of most small basics, but running in a sort of a more familiar way to people who've worked in C and Java and C#. Okay. And on that note, I think it's a good time to finish this video. You can go and look at the Hopper language playlist, which is not platform specific, and learn a lot more about the Hopper language to write more programs on this device. Right now, in terms of peripherals, this 6502 system has a serial port, it has a time API, and that's about it. And you can directly access all the memory as well, not just through there's inside the minimal API. I think there's a memory. Oh, it's not visible here. But I think we can easily see it if we just do. Let's go and have a look at memory. There we go. I'm right-clicking on things and double-clicking on things to go to them. So yeah, you can directly access, see how much memory is available. So it has allocate and free, which are very similar to malloc and free in C, and it manages that and cleans up. But if you use this interface, then it won't clean up after you in terms of actually freeing things that you created. Once you free them, it'll put them back in the free list and fix the heap up again, get rid of fragmentation. But if you just use strings and arrays directly, so these are the string APIs, all the stuff you'd normally expect to see in like C# or Java. Control backspace to go to the other one, and this is the array API. The array API is pretty simple. You make yourself an array, you set items, get items. But a good example of the array API is if you look in the benchmark. It's just the byte benchmark. They wrote it in BASIC in 1984. There's an array in this byte benchmark, flags global, and it's actually a Boolean array. And because it's almost 8K, that would be 8K of RAM, but Hopper optimizes this so each Boolean element only takes up 1 bit. And you don't have to do anything clever to do that. You just use it like an array. So it fits the whole 8K of elements into 1K of space. Anyhow, thank you for watching. And like I say, go and watch the Hopper language playlist to learn more about the Hopper language. And then I think the next video in this series is going to be on how to get up and running with the 6502 assembler. So instead of building the Hopper runtime and putting it onto our device, we're just going to write our own program and put it on the device and run it. So thank you for watching, and I look forward to your feedback.